Ladies and gentlemen, welcome to lecture number 9, as we'll be looking at digital filters. This is a fourth-year course for the 2EEE for the 221 in the School of Engineering at the University of Zambia. My name is Charles. The lecture outline will look as follows. In a short while, I'll be introducing the course, digital filters. Then we'll look at finite impulse response filters and infinite impulse response filters. Then we'll compare the two, FI filter versus IIR filters. And I'll give a brief tutorial and then I'll point you to some references that you need to check for more examples and tutorials within this course. So digital filters are basically classified in terms of recursive and non-recursive filters. And when we talk of recursive filters, these are filters that have feedback loop. They are also known as infinite impulse response filter, whereas non-recursive filters, these are filters that don't have feedback, and they are also called the finite impulse response filter. Basically, the finite impulse response filters, as you'll see later on, they only have a forward loop, they don't have a feedback loop. So those are the two types of filters that we'll be analyzing in this course as we look at digital filters. Moving further now, I want us also to point out that most of these digital filters are implemented using adders. They are also implemented using multiplier circuits, delay circuit. If you recall, in the course EEE 31 Digital Electronics, one of the third-year courses here at the University of Zambia, which I believe by now you must have covered that course. You must have learned about half adders, full adders, multiplier circuits, delay circuits. So basically those are the building blocks as we look at digital filters. Also of interest, you can implement any digital filter to achieve either low pass, high pass, band stop filter, just like it was done under analog filters. So let's look at now the details, but let's begin with the finite impulse response digital filter. And like I said, these are a type of filters that provides only the forward loop, and they are made in such a way that you have a multiplier circuit through which you pass the input x of z. This x of z basically is an input to either have the forward loop passing through the multiplier circuit without any delay component, or you may have the second forward loop to the summer passing through some delay components, and these could actually be a chain of them, a chain of delay units, and each of these will be feeding to the summer in order to get the output y of z. So the general z domain model of this type of filter is basically what is shown here in figure 1. And as you'll see here from this figure, basically we can come up with a derivation for the mathematical model, and that model will basically in such a way that you can derive the output y of z from that block diagram. You can get the output y of z, giving you a of 0, x of z plus a of 1, x of z with a delay component of -1, a of 2 times x of z with a delay component of -2. Then you've got a3 x of z with a delay component of -3, and this can carry on up to, the last up to infinite. Now you can also move on to calculate the transfer function. The transfer function from equation 1, and the transfer function here denoted by t of z, which is basically the ratio as we saw in lecture 8. It is the ratio of the output to the input. So t of z here is basically the ratio of the output y of z to the input x of z. And for such type of a filter, the finite impulse response, the transfer function is simply a of 0 plus a1 z minus 1 plus a2 z to the power minus 2, a3 z to the power minus 3. And this can carry on depending on the number of delay components that you have, multiplier circuits that you have. So basically, that's a general equation for the output y of z as shown in equation 1, and also the transfer function as shown in equation 2. So let's move on by now looking at some kind of an example. So the basic circuit, like I said, is one shown here. We can consider this diagram here as an example. If you look at figure 2, you'll notice that, in this figure, you have the input x of n, which is basically the time domain equivalent. And then you have the delay denoted by the block with capital letter T. Then you have the multiplier circuit here, which has a coefficient of minus 0.4. Then again, you have a summer here giving the output y of n. Now you notice that everything else here has been given in the time domain. Yeah. So from figure 2 here, we can write the mathematical equation to depict the output y of n as y of n equals x of n minus 0.4x with a delay component of -1 or 1. So basically what we have here in this equation is the output y of n being depicted in the time domain. But then it's much easier to resolve digital filter using the Z transform as we saw in lecture 8. Therefore, we choose to abandon the time domain and instead resort to working in the Z domain. So the first thing then we'll have to do is to convert our processing system of figure 2, which is in the time domain, to the Z domain equivalent. And that Z domain is basically shown in the next slide here. So that's basically our figure 3. If you look at our figure 3, it's a FIR filter in the Z domain. And you'll notice here that you will have now x of n changes to x of z. The delay, which was t here, changes to z to the power -1, showing the delay of -1. The multiplier remains the same, the sum remains the same, but the output again here is in the converted in the z domain using z transform as just y of z. So again, we can move on like we did in the time domain to basically find the mathematical equivalent of figure 3, and this can be shown in the next slide, whereby we have y of z in this case being equal to x of z minus 0.4 x of z, delay of z to the power -1, and then we can basically factor out the x of z, which is common here in this equation, to arrive at the equation down here. So y of z becomes x of z, which has been factored out. And then when you open the brackets here, you've got 1 minus 0.4, and then you with a delay of z to a power minus 1. And then we know the transfer function is y of z over x of z. Therefore, dividing both sides by x of z gives you the transfer function, which is t of z equal to y of z over x of z. And then this, now the transfer function becomes 1 minus 0.4 z to the power minus 1. So that's a basic example to illustrate how you can implement a finite impulse response filter. You need to, if the scenario is given the time domain, one of the first steps is to convert it in the Z domain, and then from there, you know, you can find the output y of z, and then the transfer function y of z over x of z. So let's move on to our local second type of filter. This is the infinite impulse response filter. The basic diagram or model is shown in figure 4. That's the basic model for the infinite impulse response filter. What you see from this model is that you will have the output x of z, and then you have the summer here. You still have multipliers here with the coefficients b1 to b3. And again, these coefficients can be more than that, depending on the size of the infinite impulse response filter. And the third aspect you see here, you still have the delay here. So the first block here being delay of minus 1, delay of 2, delay of 3, and all these producing an output y of z. And the other aspect, which is also very important to take note, is that this type of filter will have a feedback loop, you know, to the summer taken from the output y of z. So the mathematical equation to depict figure 4 is shown here. And what you notice is that y of z is nothing but x of z plus b1 y of z. And then you have the delay component z to the power minus 1 on the output y of z. Then plus b2 y of z. We are using y of z because this again is gotten from the output y of z with a delay of minus 2 plus b3 y of z with a delay of z to the power minus 3. And then we can move on by grouping the like terms together. And what you get is a scenario whereby you have x of z. Of course, you factor out y of z here. Y of z has been factored out. And then you can take this whole block on the left side of the equation, and then you end up having this equation here being equal to x of z. And then from there, you can find the transfer function, which is y of z over x of z, or simply t of z being equal to 1 divided by 1 minus b1 z to the power minus 1 minus b2 z to the power minus 2 minus b3 z to the power minus 3. So this basically equation 4 gives you the transfer function, while equation 3 here gives you the output y of z mathematically. So let's move on. In the next slide, basically what I'm going to show is, you know, a more detailed or practical model. And in that practical model, you notice that x of z pass through some multipliers and then some delay circuit, and it might be more detailed than the previous model we've just looked. And then the output again here, it will have more detailed multipliers. You know, it will have also some delays. So delays will be on the output side, as well as delays on the input side, multipliers on the output side, as well as multipliers on the input side. And each of these are feeding into the summer there, and then producing an output y of z. So that's more detailed, you know, infinite impulse response model. of a filter, and we can again, move on to find the transfer function for this type of a filter, and this will look mathematically as follows. Basically, the transfer function will be A naught, or A of 0 plus A1 z to the power -1 plus A of 2 z to the power -2 plus A3 z to the power -3. And this can carry on, divided by 1 minus B1 z to the power -1 minus B2 z to the power -2 minus B3 z to the power -3. So basically, this is a more general format for the transfer function. And what you notice from this transfer function is that if you are to simplify the numerator here, you will have, a function consisting of zeros. Okay, and if you are to, that's basically for the numerator, and for the denominator, you will have a function. If it is further simplified and equated to 0, you will have a function consisting more of pores. Now, that's a very, very important point to take note, because what we are getting here is that for the infinite impulse response filter, it will have both the pores and zeros, unlike the finite impulse response filter where we only saw zeros and there were no pores. We only saw basically the numerator, and there was no denominator, denoting that there were no pores. So, having analyzed this, we can now further, move on. Finite impulse response versus the infinite impulse response filter. And one of the key things to take note here is that the finite impulse response filter uses few multipliers and even few delay components, therefore it's less complex, whereas the infinite impulse response filters requires more multipliers, more delay circuits, therefore it's more complex. And with complexity means that you will have a complicated hardware, whereas because the finite impulse response is less complex, even the hardware is basically much simpler. The other important contrast to take note here is that the finite impulse response has got only a forward loop, no feedback loop, whereas the infinite impulse response has got a feedback loop. And then the other aspect also to take note is that the FIR will always be stable filter because it consists only of zeros. So therefore, what determines stability of a system is the presence of pores, and whether these pores are outside or inside the unit cycle, like we saw in lecture number 8. And because the finite impulse response filter has got no pores, it has got only zeros, it is always stable, whereas the infinite impulse response filter here, it is less stable because pores tend to make the system unstable, especially when they fall outside the unit cycle. The next difference or contrast to take note is that the FIR has got linear phase, therefore it's much easier to control as opposed to the infinite impulse response filter here, which is difficult to control because of non-linearity in terms of its phase. The other contrast is that FIR only consists of zeros, whereas the infinite impulse response consists of the pores and zeros. And these pores basically are very key in determining system stability. So those are basically the contrasts. Let's move on. Now look at a few tutorials. You notice in this tutorial here, depicts the presence of pores and zeros. Therefore, this is a good example of an infinite impulse response filter because of the presence of pores there, zeros, and the presence of pores at the denominator. So we can draw from here the Z domain version of this block diagram, and also you can express the output in the time domain. That's what I need here. You can also express the input in the time domain, even when everything else here has been given in the Z domain. And then find the unit sample response for this filter and just consider the first 4 terms. For the hint, I have given Bob Mendes one of the recommended books. Check on page 36, you get a hint of how to go about this tutorial. So next, let's have another tutorial. In the next tutorial here, basically is again another example of the infinite impulse response filter, in the sense that you'll have this part, which is almost similar to the FI part, but there's a feedback loop here with the delay of -2, and in this one there is no multiplier on the feedback loop, so we can still save the one just before the output of 0.4. Therefore, you can still calculate the output and also determine the transfer function and also determine whether the system or this filter is stable. The next tutorial, again, I would want you to look at this one. This is an example of the FIR filter. And all I'm asking in this tutorial is for you to basically find the sequence at point A here, find the sequence in the time domain, find also the output in the Z domain, and then finally find the output Y of N in the time domain. Then this basically marks the end of this lecture. Thank you very much for your attention. You take note, I have given Bob Mendes as one of the recommended books, but you can also use the second text here as part of the book. It will be very useful in this course.